So the actual molar volume of the methanol water mixture is lower than what you would expect from the ideal solution. Okay? And the reason for that ties back to what we talked about when I first introduced the concept of ideal solutions. And so water and methanol, there's this, they're not the same molecule, right? First of all, they have different sort of interactions going on, and also their molar volumes are very different from one another. The molecules have different sizes. And so due to this combination, let me rewrite that, it came out terrible. Combination of differences in molecular interactions and sizes, whenever we add a drop of water to methanol, the effective volume water added to methanol is smaller or is less than the volume of the pure water drop. Okay. Now, so that's just what happened. That's physically what's happening. Every drop of water we add, once it goes into that mixture, the effective volume of that drop decreases or is smaller than what the pure drop was like. And so we see that the change in the total volume of our system is smaller than what we would expect if we had the ideal solution. Now, to be more quantitative about this idea, what we could do is we could say, that we're looking at the total volume change of the mixture. So, volume of total mixture. So delta V, right? And the total volume change of the mixture is essentially going to be equal to the effective volume, molar volume, of each of our H2O drops times the number of moles of H2O we add to the system, right? So molar volume is, volume over moles, and then this is moles, right? So that in the end we just get volume. Okay? And so essentially that's what the total change in volume of the mixture is. It's just going to be a product of the effective water molar volume times the moles, the amount of moles we're actually adding to the system. If we rearrange it, we get that the effective volume of H2O, molar volume, is equal to delta V over delta N H2O, right? That just comes from the algebra. But now what we could do is we could take the limit of that ratio. So the limit of delta V over delta N H2O, and we take it in the limit as N H2O goes to 0 at constant T, P, and also constant moles of methanol, right? We didn't add any moles of methanol to the system. We only added moles of water. So holding all these things constant, if we take the limit of this ratio, mathematically what we'll get back out is a partial derivative of the volume with respect to the moles of water at constant T, P, and N methanol. Okay? And so this effective volume of the water, once it's in the mixture, could actually just be calculated as the partial molar volume of the total mixture, or the partial volume of the total mixture, with respect to NH2O. Okay? All right, and so mathematically, that's how one would determine the effective molar volume of some substance B added to a mixture. But we could be more general about this math. Okay? And so in general, for any extensive property, if we take the partial derivative of the extensive property for the entire mixture with respect to the moles of one component at constant T, P, and for cases where J indices is not equal to I, so Nj is not equal to basically all the other components that aren't the ith component, what we would get is some sort of effective molar property for that component once it's in the mixture, right? And the nomenclature, or the way we're going to write this, rather than always writing tilde effective, is that we're going to write this as mi bar, where the bar is above. And this sort of term, this sort of property in thermodynamics is known as your partial molar quantity, right? And so up here, we define the partial molar volume of water in our mixture. But you could also have partial molar enthalpies, partial molar entropies, so on and so forth. And I want to say that in general, your partial molar quantity for some component, right? So this is not pure. This partial molar quantity is not equal to the molar property of the pure component. Remember, this bar here tells us that this is the effective molar quantity once that chemical species is inside the mixture. And the tilde here is just referring to the pure component when it's just by itself, okay? So in general, these two things are not going to be the same. And they're only the same when you have like an ideal solution or something, okay? So be very careful about that. Make sure not to automatically assume that these two things are equal, okay? All right, and so for emphasis, I want to say that you can have a partial molar quantity for any extensive property. And so, as we saw with volume, you could have a partial molar volume with enthalpy you could have a partial molar enthalpy. You could also have with entropy a partial molar entropy. Okay? And I want to emphasize that what you're taking the partial derivative of is the quantity for the entire mixture. Okay? So you take the partial derivative of the property for the entire mixture with respect to the moles of a single chemical species or single component. The last partial molar quantity I want to write out is the one for Gibbs energy. So you would get a partial molar Gibbs energy. But a lot of times this partial molar Gibbs energy is written as mu I. Okay? And the reason for that, it also has a special name too. This mu I is commonly referred to as the chemical potential of a species in a mixture. Okay? And so the reason that mu I gets its own letter and its own name is that it's the most famous of the partial molar quantities, because basically, as we saw in chapter 7, for a system if we just had like a single chemical species, for the system to be at equilibrium and have different phases coexist, the molar free energies of those two phases would have to be equal, right? In our case, when we're dealing with mixtures, not only do the molar free energies for a single component, the molar free energies in different phases have to be equal, but that statement has to be true for all the chemical species in the system, all right? And by convenience, it turns out that if we just the equilibrium criteria for multi-component mixtures is actually going to depend on this chemical potential term here, okay? In fact, I should probably just take some time to mention, I'll write it out here, that mu I serves as one of the stability / equilibrium criteria for the phase behavior of mixtures. Okay? And so if you had some sort of system in this box, and you had two different phases, alpha and beta, with a mixture, you may have your two components both in the alpha phase and in the beta phase. And so for the phases to be stable, your equilibrium criteria would be this: that the temperature of the alpha phase is equal to the temperature of the beta phase, the pressure of the alpha phase is equal to the pressure of the beta phase, and then the third criteria would have to deal with the chemical potentials, such that the chemical potential of species 1 in the alpha phase has to be equal to the chemical potential of species 1 in the beta phase, and separately, the chemical potential of species 2 in the alpha phase has to be equal to the chemical potential of species 2 in the beta phase. And I want to emphasize that this is true and this is true, but saying that the chemical potential of species 1 is equal to the chemical potential of species 2, that's not true. That's not a generally true thing. All right, so we'll talk more about that later. But essentially, the main point I want to emphasize is that these chemical potentials turn out to be useful if we want to study the phase behavior and equilibrium behavior of our mixtures.